Okay, so what we have been discussing is pair of random variables, right? Pair of random variables. So we have pair x and y. So there is a random experiment. X measures something. X measures something, some value corresponding to that experiment, and y also measures some value corresponding to that experiment. And then we said, okay, we can have a joint PDF, which is a function of x and y. So the x is taking the value small x, capital X is taking the value small x, and capital Y is taking the value small y. And we have a function here. Under certain conditions, this will represent a joint PDF for xy. And then we said, okay, if we know this joint PDF, from there we can calculate what is called the marginal PDF. Marginal PDF. So which is, if this is the joint PDF, then we can calculate it's called g of x. Let's say that's the PDF of x. This is the PDF of x, or we can simply write f x for x. And there is a PDF of y, PDF of the random variable y, which we may denote it as fy y. So these two are called marginal PDFs. And then we introduce the concept of like how x and y can be correlated, whether the values of x has something to do with the values of y text. Okay. For example, we said our model example was like, suppose capital X measures the height and capital Y measures the weight of a student in this course. Or you can assume that you had already two class tests. So capital X measures your score in the first class test, and capital Y measures the score in your second class test. And the question would be whether they are somehow related or not. And then we studied the concept of what is the covariance, how they are varying. And before that, we defined also what is called product moment. So this is covariance. So we denote it as co x comma y, the covariance. And then we started talking about correlation coefficient, the normalized covariance. You can say the normalized version of this value. So correlation coefficient, which you denoted as rho, or you can say rho of xy. And then we introduce what is called the conditional random variable. So since we have a pair of random variables here, so we can say marginal PDF given y assumes some value small y. So then this is also a random variable, and we call it the conditional random variable. Conditional random variable. Random variable. And then we said, okay, since it is a random variable, we can also talk about its mean and its variance. So then we define the concept what is called conditional mean. So there can be two conditionals mean. One, you can write expected value of x when some capital Y is given to you. Capital Y is called, let's say, small y. You can write it as this also, because this expectation is corresponding to the random variable x, capital X. So you can also write small x here for the expected notation ex, and then also you can say ey, which is the expected value of y given that capital X assumes the value small x. And then we also called what is what is called conditional variance. Conditional variance. So it said, okay, variance of x given y equal to some small y, or just variance of y given capital X equal to some small x. And then we have seen how, okay, so we also have seen that this will be a function of y, this will be a function of x. If x and y are treated as small y and small x, they are treated as variables. Otherwise, if you give some value, for example, y equal to 2 or 10, whatever it is, or x equal to half or 5, whatever it is, then you will of course get a number because that's the expected value. Similar thing is also going to happen for variance. And then we also defined, okay, that if this y, keep it as a variable, then it is a function of y. Here it is function of x. And then again, we can define some random variable. And we have seen some applications of those results. And here also, we have seen some applications of these results by computing, let's say, this the PDF of sum of the random variables and so on. And of course, we introduce the concept of what is called independent random variables. So like when do you say x and y are independent? Okay, so for example, if covariance is 0, then the correlation coefficient is 0. Then we can say that x and y are independent. Or you can say if x and y are independent in general, that in this joint PDF and we factored as a product of the function of x and the function of y, and the function of x will be the marginal PDF corresponding to capital X, and the function of y will represent the PDF corresponding to the random variable capital Y. So this is how we defined what is called the independent random variables. And we said, okay, independent random variables will have a lot of applications when we'll talk about statistics. This is what we have done till now. Now today, what we'll try to do is, first, we'll talk about the concept of functions of random variables, or functions of a pair of random variables. Functions of a pair of random variables. And what is that? Random variables. Okay, first, let me just recall that we have discussed what is called function of a random variable when it was a single variable. For example, suppose x is a capital X is a random variable, then we talked about a random variable which is some function f of, let's say, capital X, some functions, let's say x squared plus 2, or something like log x, or we talked about, okay, square root of x, mod x. Okay, these are all functions. Okay, these are all functions. So we also had some attention about this function, x minus mu by sigma, which is standardization of capital X. Okay, we also defined, and it has some use. We also have seen from normal to standard normal, and we also have defined to connect to this chi-square random variable. So we talked about square of this. We talked about this. So these are, let's say, some functions of x, okay, that we have studied. Now, what we'll do today in the beginning is that suppose we have a pair of random variables x and y. Then what we want to discuss is, suppose we have a function of the both random variable x and y. For example, so I can write this as f of, okay, so if we are denoting as PDF, so let us say a capital is also for CDF. So let me write some functions like k. So we can write k of xy as a function of this. For example, it could be x plus y. This is a function of x and y. It could be x times y. It could be x divided by y. It could be minimum of xy. So these things are said, but we did not discuss formally. So I think I solved some problems regarding this, but we did not formally define what is called a function of a pair of random variables, or we can say max value of x and y. These are all random variables, which is a function of x and y, or we can say, let's say, square root of x squared plus y squared, and so on, or just x squared plus y squared. Okay, so yeah, so the idea here is, Suppose you know the joint PDF of the pair of random variable x comma y, then the question will be, if some function is given to you, let's say kx, k of xy is given to you, then what is the distribution or what is the PDF of this random variable? Okay, this will be very much useful when we'll talk about statistics again. Okay, I mean this is a primary concept. I think which today we'll introduce. Okay, why this is very important. Okay, we'll talk about that. In fact, we'll talk about much more than this. So we can have, let's say, n random variables, x1, x2 dot xn, and then we'll define a function. Okay, so one valued function. So these are all real valued function. Okay, x plus y, x by y, x times y. These are all one valued function. I mean, given a pair of values x and y. So here, for example, this could be x and y. From here, we are defining this k, which can take the values on the real axis. Okay, so this is one valued function, a single valued function, or real valued function, as you can say. So just to, so the idea here is what is the PDF of k of xy? Okay, that's the idea. That's the goal here. Now just recall, because is this I said when we talked about function of a single random variable like this here. Okay, so there we proved the theorem. Okay, let's just recall the theorem. We said, suppose x is a continuous random variable. For discrete, it will be very simple. So you just have to, for example, x assumes some values, y assumes some values, and then these values will be something but you just take the corresponding values and sum it up or divide, whatever the definition is. Accordingly, you just find it out. So it will not be a very difficult task, but when x and y are continuous random variables, okay, or x is, let's say, a continuous random variable, then it would be a difficult task. So we need to prove some theorems which can be useful for deriving the PDFs of the functions that we are defining. So what we did for the case of single variable, we said, okay, if capital X is a continuous random variable, and let's say we have a function y, which is some t of x. This is a function, and we assume that it is either increasing or decreasing. Then we can talk about PDF of this y, let's say this capital Y, or let's say PDF of this t of x. There is a function of x, this random variable, and we defined it like g of y. We proved it actually that it is mod of dx dy. Okay, and then f of wy. And what is this w? This function w is the inverse of t, where x equal to wy. Okay, is the inverse. It's the inverse of t, or you can say tx. So what is happening here? You have some x, that x can take some values here, small x, let's say. Then you can have t, which can give you the value of y, and this is the value. This is the function which will map it to this, which is w. So inverse has to exist. So this is how we have defined. We have proved this theorem that if I have a continuous random variable capital X, then I can have, and I have a, let's say, an increasing or decreasing function t, then we can compute this PDF of this function y, okay, using this formula. So what we have to do first is that since this is given, so we have solved some problems also. So if suppose this is given y equal to t, so t is given, how it is given, for example, x square, x cube, whatever it is, then you have to write x in terms of y's in order to compute w. So once you know that w, then you can just take the derivative of that dx dy. Once you write x in terms of y, then you can take dx dy, you'll get some value. Okay, you'll get a function, take the modulus of that, and then if you know w, so you know f, so you can write f of w and y. So this f here is the with PDF f, let's say, with PDF f. Okay, so this is the thing we have proved, and I also said that we will not prove. Similarly, it can be proved. It can be extended. The proof can be extended. The way we have proved it can be extended for the case of pair of random variables. So here we will not prove it due to lack of time, but we'll state what is it. Yes.
So what happens is there is a maximum and minimum point in that function y equals to tx.
This is in general function. This is just a function. So here we have this xy. So here the case was different. Okay, here we have a single variable x. Now here we are taking this capital, so minimum of x or y or the maximum, let's say, it will assume some value of x and y, right? Let's say x is, I mean, for the case of discrete, let us say. We'll prove the theorem for continuous case.
Sir, I have a doubt in that previous theorem, like not for the
Yeah.
bivariate. For single variant, I have a doubt that y equals to tx. If that is there is some maxima minima in that, then
So
we can also write inverse and
here the maximum, see, y is equal to tx, and if you say t is the maximum of x, that is what you are saying. Then that's
no,
a
sir.
single valued function.
Sir, you are saying that it should be an increasing function or decreasing function.
Here,
But I am
okay,
saying
yeah.
that what happens if there is a maximum or minimum, like it will change, it's increasing or decreasing at a point.
I didn't get it. So let's say I have this x, this is the x, and this is the y. Okay, so if it is discrete, it is assuming some values here, let's say. Now for each x, there will be some y, this one, this one, this one. Or for the continuous case, it could be just, let's say, this is like, let's say, this is where the function x is non-zero. Otherwise, it's, let's say, 0. So this entire interval. So here you can have some kind of a function. Let's say this is the function. So this is what is t of x. Yeah, there can be maximum. For example, here this is a maximum. This is, or maybe here it is a minimum. This is this point there is a local minimum. Okay, here it can be a local minimum, a local maximum. Here it is a global maximum, and so on. So this function is not increasing or decreasing. But the theorem we proved when this is increasing or decreasing, because we have to have the inverse. But anyway, so inverse does not, existence of inverse does not mean that it is increasing or decreasing. But we need the concept of increasing or decreasing that we used in the proof of the theorem. That if it is increasing or decreasing, then only we can prove that theorem, that this particular theorem. We proved it. Somehow we use this. I mean, in fact, I asked this question to you guys, like where did I, so I derived somewhere in between, I used an equality, and then I asked you why this equality is valid. And the answer, some of you gave the answer that since it is decreasing or increasing. So it is required in the proof. So this theorem is not valid if t is not increasing or decreasing. So for example, I can assume like this is kind of a function, like where this is a non-zero, and let's say this is some increasing function. It can go very slowly like this also. Increasing. It could be decreasing as well, like this. So there is some value here, which I had it is taking maximum, or here somehow it is maximum, depending on the curve. I mean, depending on the function, whatever it is. Is it okay now? So this is x. So max will assume here or here, depending on whether increasing or it is decreasing in this interval. So this is tx. You can say this is t, or this is t, this is tx, whatever. Is that okay, or you have some any other doubt?
So like if a function have maxima, minima both like in above curve, then that theorem should also valid.
This one, this curve.
Yes, sir.
No. Then the theorem is not valid. So here we are assuming that t is either increasing or decreasing. Then we can conclude to this one.
Okay, sir. Okay. Got
This
it.
theorem is not valid when it is not increasing or not decreasing. Because in the proof, if you just watch that video, then you'll see that I use somehow this property that is increasing or decreasing for some probability.
Yes, that time
Yes.
I know. You have described if it is it has
Sir,
maximum, then what will happen? That's why
Yeah.
I asked.
sir,
But here, when you are defining, I'm coming to this. So here, when you are talking about x and y, this is a two-parameter function. Okay, so we can talk about minimum or maximum. Yeah. So if somebody is saying something, yeah, please go ahead.
sir, but in that case we can find it uh, for part for part like from x1 to x2, we can define some domains like for x1 to x2 that is decreasing, and for that we can apply these formulas. So
No, the thing
like
is,
from for that part,
yeah.
if this is
So
decreasing from there to there, this will be the PDF according to what function has been given, and from there we can say
yeah,
that.
yeah, yeah, yeah. So the idea is in that case, you have to use it partwise, and this is what is called piecewise increasing or decreasing function. In fact, some problems can be there where you don't need increasing, decreasing, you don't need to use this formula, for example. Still, you can find it out. But when you are proving a theorem, okay, so we have to make some. So in a theorem, what happens is, so theorem is a statement. Okay, what is a statement? There is a difference between a statement and a sentence. Okay, I think I said this earlier also. The sentence is something which is a bunch of words which has some meaning, which you understand. Okay, for example, I can say, today it may rain, although it is raining today anyway. So I can just say, tomorrow it may rain. So it is a sentence, but it is not a statement. Why it is not a statement? A statement is a sentence which has a definite meaning. That means if I say it will rain today or it will rain tomorrow, then it has a meaning. So that this is like a logical thing. So you can take either you have a statement or you have a sentence. It is either true or it is either false. So if it is, then it becomes a statement. So you have a definite meaning. But if you are lying in between 0 and 1, so it is not true, not false, you don't know, then it cannot be treated as a statement. So whenever we prove a theorem, so we always say statement of the theorem. We don't say the sentence for the theorem. We say it is a statement for the theorem because it has a definite meaning. And here the meaning is, if this is true, then this is true. Okay, so it is if then. So if it is not valid, we do not know whether it will be true or not. We don't know. Okay, but if this first part is true, then the second part is true. Now we can say, okay, using this, we can prove other results. That is okay, perfectly fine. But as long as this theorem go, we can just, if we have increasing function, then we can have this. Now you may say probably, okay, this part, for example, if I take this part, this particular part, probably the function is increasing. So I can apply the theorem here. Or this particular part, let's say the function is decreasing. I can apply this thing, the theorem here. It is perfectly all right. But you can have functions where this function is so zigzag functions. Okay, I mean, you need not be able to plot it like, let's say, sine 1 by x kind of a thing. Okay, so where this function is like, okay, so it is like this kind of a function. Okay, this kind of a function. So then you do not know what is the domain where it is increasing, where it decreasing. Yeah, that is what I'm saying. If this condition is not true, it does not mean that it is not increasing or decreasing. It does not mean that it will not be able to find a PDF. What we are saying here is, if this is increasing or decreasing, then this follows, the second part follows. You can find a PDF. But if it is not increasing or decreasing, there may be some different means to find it out. But this theorem at least is not valid in general because it is not increasing or decreasing. So we cannot say. But you may find out possibly using some other technique. Okay. Yeah, so yeah, this is what it is. So now I'll just state the theorem for this function of pair of random variables. Okay. So let us assume here also let x, y be continuous random variables. Measure some things, variables. Now let's say with the joint PDF, we know also the PDF with the joint PDF f of xy. Okay, and let we have two functions. U, which is a function of, let's say, x and y, that's a p, and v is a function which is q of x and y. These two are functions of x and y. Okay. Now what I'm saying is, the theorem states, if so, this is a function of this means we have a function a p of xy, and if you put let's say capital P of xy, when you put small equal to capital X and y equal to capital Y, then this is the function. Similarly, here the underlying function is, let's say, q of xy. Okay. Now the theorem says, if pxy and qxy have inverses. Inverses in a sense, inverses. That is, in this sense, that is, x can be written as some function of u and v. The same thing, like here we had the function t, and then we had a function w. What is that w here? If you write y as t of xy, if you write y as t of xy, then here you are writing x as w of y. So this, in this sense, it is the inverse. Okay. So then what happens is, if the inverse exists, so x can be written in terms of u and v, and y can also be written as some, let's say, function of u and v. Then the joint PDF, of u and v, this pair of random variable, is this g of uv, which is equal to mod of j. I'll tell you what is mod of j, and then f of r of uv and s of uv. Same way. See the same here. There was f of wy, here. You see f of wy. Here it is nothing but f of ruv, because there are two variables. So f is the function, the joint PDF. So it has two arguments, x and y. So f of ruv comma s of uv, and this mod j. So j is the Jacobian here, which becomes a, actually here you had the modular. For the case of single variable, it have modular of dx dy. It is also the modulus of the Jacobian. I think you know from math 1 that the way we calculate derivative for a single variable function, we cannot do it for multivariate function like two parameter functions. Okay. So many things are, so first, for example, we have to first test whether function, there is no concept called derivative of a two valued function. Okay. So yeah, first we need to check whether it is differentiable or not. And then if it is differentiable, then we can have a Taylor's extension and so on, which we have probably have studied. And then we talked about, okay, what is the meaning of this Jacobian in math 1. So I will not repeat that here. So this j, mod value of j, j is the determinant of this 2 by 2 matrix, del x del u, del x del v, del y del u, and del y del v. So same thing here, what we had earlier for the case of single variable. There only we had one variable, let's say u, that was the function t. So y was there. So we had to write mod of dx dy. Here mod of the determinant of the Jacobian here. So if we just compute this, this will be del x del u times del y del v minus del x del v del y del u. So this is the Jacobian of this function. That's it. This is the PDF. This GUV is the PDF. So proof is exactly similar. Okay, like the one variable case. So here you just have to remember that it is just an extension of this formula. So even if you remember just this formula, then you can find out, okay, what should be its generalization or extension for two parameter function. So the dx dy, this derivative will be replaced by Jacobian, and since there are two arguments for f, here f was a PDF, there is a joint PDF. So accordingly, you have the inverse one, like w is the inverse here. There you have two inverses, r and s. So this is how it is defined. Okay. So that's how we can find the PDF. Okay. So let us first solve a problem. Okay, and then we'll see like how it can be useful. Problem. Suppose xy are random variables. With PDF or the joint PDF. Let's say something like f of xy is equal to 8xy when 0 less than x less than y less than 1 and 0 otherwise. Now question is find the joint PDF, or you can say joint density also, joint PDF of u, which is a function of x and y. Let's say it's x divided by y, and v, which is y. Okay, so I have to find a joint PDF of this. Okay, so how do you proceed? We have these functions, u is equal to x by y, and v is equal to y. So we first have to write x in terms of uv and y in terms of uv. So this implies what? X equal to u times y, but y is equal to v. So this is equal to u times v, as simple as that. And y is of course equal to v. So now we have written x in terms of uv and y in terms of uv. Then we can find out what is the Jacobian, which is del x del u del y del v minus del x del v del y del u. So del x del u will be like v, right? Yeah, v times del y del v is 1 minus del x del v is again u, del y del u is 0. So this is just v. So then according to the formula, then the joint PDF of u and v is nothing but mod j f of r uv, the function of uv, and s of uv. So then this is mod of v, and then f of uv, and this is v. And we know f of this is 8 times xy. So this 8 x and y means here uv times v, so it's uv square. But now here, when you're applying this, see, this function is defined when xy is like x is less than y less than 1. So then this is the PDF only when uv is less than v, okay, and less than 1. So now since, so you have to find out for what values of this it is non-zero. Others, for other cases, it will be 0. Now since 0 less than x less than y less than 1, so we must have 0. So this implies 0 less than uv less than v less than 1. Then what can we say from here?
Sir,
0. Yes.
it should be v cube now.
What is,
So in
oh,
place
okay.
of
Yeah. Sure. XY. No. Yeah. Sorry. You're right. So yeah. So 0 less than uv less than v, or you can say 0 less than v less than 1. So this is the domain where this is the PDF. Okay. So from here, what can we say? 0 is less than v less than 1, and 0 less than uv less than v. They can say, says u should be less than 1 and 0 should be less than v less than 1. So now we have the PDF. So PDF is GUV, which is 8uv cube when 0 less than uv less than 1 and 0 otherwise. So this is just use of this formula. Okay. Now let us solve one more problem just to understand how to use this formula. Okay. So suppose now I'll focus on independent random variables. Okay. Suppose this given random variables for this formula. Okay. So xi could be anything. I did not say that they are independent continuous random variables. Suppose they are independent, then what happens? Okay. Let us see an example. So suppose x and y are independent continuous. They're of course continuous when you are applying this particular theory. They're independent continuous random variables, continuous random variables. Okay, with let's say the PDF. So with let's say they have the same PDF. With the same PDF, so they are IID. Okay, independent and identically distributed. The same PDF. So meaning they are x and y are IID, independently and identically distributed. Okay, then okay, so the PDF is, let's say, this, which is e to the power minus x, and let's say 0 less than x less than infinity, and 0 otherwise. Now the question is, let's say, find the joint PDF, joint density or joint PDF of this u, which is a function of x and y, let's say it is x, and b, let's say this is a function 2x plus 3y. Okay. Okay, so let us see. So our first idea is, okay, so these two functions are given. So u is equal to x, u is equal to 2x plus 3y. These two are given. So we first have to express x in terms of a function, in terms of u and v, which is already given, by the way, and y also you have to write in terms of u and v. So this implies x is equal to u and v is equal to what? 2 times x. So x is equal, so 2 times u, 2 times what is called u, plus 3 times oh, so can anybody tell me what will be this one? You'll find y here.
V minus 2u by 3.
What is that? V
minus
2u by 3. Okay, so then this will be what? So this is 3 by 3. So 2u minus 2 by 3 u. Right? Am I okay? Is that okay? The calculation. See, I do a lot of calculation mistakes. So okay, let me just write it. 2u plus 3. So this 3 will get cancelled or what? V minus 2u. What is that? Is that okay? From here you can find out what is y, right? Y will be v minus 2x by 3. Yes. So this will be something like what? 3. No, this will get cancelled. V. Is that no? What I am doing here?
Sir, you are writing v again,
Sir,
sir.
we have to
V,
find why I am saying you
sir,
about the
y
value.
equal to v minus 2u by 3, he said.
Y is equal to what?
V
Why?
minus 2u by 3.
Oh, okay. Sorry. Yeah. So what? Y is equal to this. Okay, what is that? V minus 2u by 3. Okay, this is what you said. Yeah. All right. Sometimes I do a lot of mistakes. Yeah. So this is I can say 1 by 3 v minus 2 by 3 u. Okay, got it. So this is the way you can get this. Okay, yeah, there's x and y. Okay, so then we can compute. The Jacobian. Once you have this, the formula of Jacobian: del x del u del y del v minus del x del v del y del u, which will be what? This will be del x del u. X was what? X was u. So it is 1 times this will be del y del b 1 by 3 minus del x del b, it will be 0 times minus 2 by 3. So which is what? 1 by 3. So once we have that, then we can compute that g of uv is equal to what? Mod j f of ruv and suv, which is 1 by 3 we got, and f of r is u, right? Yeah, x equal to u. So u comma 1 by 3 v minus 2 by 3, yeah, u. So we know, so this is 1 by 3 e to the power minus u times e to the power minus 1/3 v plus 2 by 3 u, which is 1 by 3 to the power minus u plus v by 3. Now, what we had x and y. X and y are lying between 0 less than y less than infinity, 0 less than x less than infinity, because it's the same PDF. They're independent. Okay. Why did I write this? They are independent. So f of xy is nothing but fx times f of y. They're independent. So I just multiplied this. So now 0 less than x less than infinity. That is why it is valid, and 0 less than y less than infinity. So these are two things which are given. So this means what? 0 less than u less than infinity. Okay. 0 less than b less than infinity. Right. So anyway, so you can do this. Yeah, this is the simple application of this formula. Okay, using this formula, you can do it. Now, let me give you one more example. Let's say, okay, let's say one more example. And from here, you have to observe something from this particular example. Let xy are IID with fx is 1 by square root of 2 pi the minus half x square minus infinity less than x less than infinity. And let u is equal to x by y, the same function, and v is equal to y. The question is, what is joint PDF of uv, and let's say what is the marginal PDF of u. So what is the PDF of u? Can anybody tell me what is this distribution? Does it correspond to some standard distribution which is studied?
It is a standard normal.
Okay, it is standard normal. Now let us see what happens to this joint. So here also same thing, u is equal to x by y, v is equal to y. Solving this, we get x equal to uv and y is equal to v. So this is the correspondence. Then we can find the Jacobian. I think we have calculated the Jacobian earlier because we are considering the same function. Jacobian here was v, the same function, x and this. Jacobian was v. So let us just calculate and put it here. Jacobian is v. Now, then what is the PDF? So what I'm saying here is, now x and y, if they are standard normal IID, okay, so they are independent standard normal distributions, then what is a joint PDF of u and v, where u is equal to x by y, v is equal to y? I want to show you that this will follow some distribution, okay, which you probably already know. Okay, let us see, or maybe the distribution of y, which you probably know. So what is this? This will be mod j times f of ruv comma suv. Okay, so this is mod v, and this is independent. So fxy, it's fx times fy. So this will be fx will be nothing but 1 by square root of 2 pi, because this is standard normal r square uv, and this is e to the power minus half. Okay, 1 by 2 pi will again be there, so it is 1 by just 2 pi, and then this is s square uv. So this will be then what? R is uv, I think, right? R is uv and s is v. So this will be mod v times 1 by 2 pi e to the power minus half. You can take that common. R square will be what? U square v square plus v square. Okay, you can take v square again here. So this is mod. So mod of v times 1 by 2 pi e to the power minus half v square u square plus 1. So this is a 2-parameter function. Do you think it is familiar to you somehow? Okay, here I must say that it will, you can show that this will also be. So it is not familiar to you because I did not give you examples of specific bivariate distributions. Okay, like the way we have studied Bernoulli, that was a single random variable. Now, what is the joint PDF if I have two Bernoulli random? We have studied PDF of, let's say, Poisson, okay, of random variable. But if I have a pair of Poisson random variables, okay, then what is the joint PDF? Or suppose we have two normal random variables, then what is their joint PDF? The specific distributions we have not studied yet. In fact, we will not study in this course, okay? But you can find it in different books because that will take a lot of time. But we will mention, okay? We will mention what is a joint PDF for normal random variables. That will do, okay? So just remember, try to remember whether this will have some kind of a reflection in the formula of joint PDF for normal random variables. So meaning when x and y are both normal random variables, okay, or maybe x and y have a joint PDF which looks like normal, and hence we'll call the joint PDF is a normal PDF. Okay. Okay, so this is what it is. Okay. Now, what is the marginal of u? What is u? Let's say G1 or so GU. I want to find out u. So how do you do it? What is the formula here? From this PDF, I want to find out the PDF of u. So what do you do? So the PDF of x by y, basically. This is what I'm going to find out now. So this is another way to find out the PDF of a function of x and y. Okay, so here first we have u and v. From there you are finding a marginal or the distribution probability PDF of u. Okay, or I could have just asked you that forget about this v part here. So this u is given to you x plus x divided by y. Then what is the PDF of u? Okay, so then probably you also have solved this problem this way, assuming that v to be equal to y, and then proceed the similar way, and then find the marginal of u. So basically, this pair of this PDF, joint PDF, is given to you. From here, I have to find out the PDF of marginal u. So what is the formula for marginal u? Does anybody remember? From the joint, how to get normal? How do you get marginal?
Sir, we will. Yes, sir. Sir, we will integrate from minus infinity to infinity. G U V dv.
Good. So once you do that, this is so in this probability course, you have to use a lot of integrations. Yeah, so this is now the case. Can anybody tell me what will be this one? Can anybody find it out? Okay, let me just write it one line. This is mod of v 1 by 2 pi e to the power minus half u square, and then v square plus 1. Oh, I think it was v square, and this is u square. Yeah, u square plus 1. Then this is dv. Okay, so there is a mod v term here. So how we have to get rid of this mod. So then how do you do it? So this mod be equal to either minus b or plus b. This will be minus b when it is from minus infinity to 0, and it is v when it is 0 to infinity. So this is minus infinity to 0, then it will be minus b. 1 by 2 pi e to the power minus half v square u square plus 1 dv plus 0 to infinity, and this is v 1 by 2 pi. I should have taken 1 by 2 pi out anyway. Half v square u square plus 1 dv. So now it is easy. Can anybody tell me what will be this one? So you can treat this as a constant, right? You can treat this as a constant because u is not varying, only v is varying. What will be this one, this value? You can tell me.
So it's gamma 3, I guess.
No, it will be a function of u, right? I mean, you are saying the final answer, or what are we saying?
So I'm saying the value of integration. It should be 2 times gamma 3, like divided by u square plus 1 by 2 pi
So
into
the
u
final,
square.
you are talking about the final answer,
Yes, sir.
but that should be function of u, right? U is not varying here. U is constant.
I said 2 times gamma 3 divided by 2 pi u square plus 1.
Divided by pi.
2
Times,
pi
okay.
into u square plus 1.
Okay, so 2 will get cancelled. What is the value of gamma 3? Gamma n is equal to what?
N minus. That's
Yeah.
2.
So how do we get it? So what is this value?
Two by pi u square plus 1.
2 by pi u square. Does everybody pi u square plus 1? Does everybody agree with this? Anybody has to say anything about this? I think this is not perfectly all right. So this will not be
Sorry,
true,
sir,
but
I have not taken the proper substitution. I have to
yeah.
do.
Okay. So what is the final answer?
Sir, I am
I think
getting
this,
1 upon pi into
Yes, sir.
u square plus 1. I'm not getting 2.
yeah,
Yes,
I
sir,
think
same.
this, yeah, I think this is the correct answer. Yeah. Now, can anybody tell me what is this distribution? Okay, I'll write it, and then you can verify. This U is Cauchy distribution with the parameter 1. You can go back and see what is the Cauchy distribution that we have talked about before. So basically what is happening here is if X and Y, they are standard normal, independent standard normal, then X divided by Y is Cauchy. So this is again a connection between different random variables. So I'll just make a remark here. That if X and Y are independent normal random variables, then okay, the quotient, standard normal I should say, not normal, standard normal. The quotient X by Y is Cauchy. It's Cauchy random. So this is just an observation. Okay. However, the converse need not be true. Okay. I mean, if X by Y is Cauchy, it does not mean that X and Y are. So that's why I always say. Okay. Anyway, so if X by Y x divided by y is Cauchy, it doesn't mean that x and y are independent standard normal. In fact, I can give you example. So okay, however, the converse is not true. Okay, for example, if x and y, okay, have the or x and y are independent random variables with PDF, same PDF. Okay, fx equal to, let's say, square root of 2 divided by pi times x squared by 1 plus x to the power 4. I mean, you can just check. Okay, this has no importance, but I'm just telling you that whenever you have a theorem, it's a statement, okay, and you always have to consider the question whether the converse is true or not. Okay, this is the way mathematicians think. But anyway, so this is just an example. Then you can see that if we take x and y this way, then x divided by y is also Cauchy. But of course, x and y, they're independent and they are not standard normal. But if x and y are standard normal, then x by y is Cauchy. This is important. Okay, now let me give you another problem. So whether you can see. So this theorem has a lot of applications actually. This is what I'm trying to tell you. Suppose x and y, suppose x is Poisson, lambda 1, okay, and y is also Poisson. This is lambda 2. The mean is lambda 1 and lambda 2. And they'll suppose they're independent. Suppose and x, y are independent. Now, my question is, this is also a very standard result which we'll use again in statistics. Okay, so suppose x and y, and these are Poisson, and x, y are independent. Then question is, what is the PDF of x plus y? How do you solve it? Sometimes what happens is, when this kind of questions are there, like you have to find the PDF of some function of x and y, you consider two functions uv, and then you kind of marginal as this one. For example, here I can state u is equal to, let's say, x plus y. By the way, you can solve this problem other way as well, like I said before. For example, if you know the NGF, the moment genetic function, from there you can find out what is the distribution. Okay, so in fact we have proved this theorem, like m of x plus y. What is that? When x or y are independent. Okay, this will be product of x and y, right? So those things we'll see. Okay, maybe we'll see it later. Okay, so x plus y. Let's say u is equal to x plus y and v is equal to x. And then we'll try to find out what is the joint distribution, and then we'll find out what is the marginal distribution of u. Then we can find this answer. Does anybody have any clue? Okay, so let me just say x equal to v, and y will be equal to what? Y will be equal to u minus x, which is u minus v. So u minus v. Okay, then we can find the Jacobian. Jacobian is with del x del u, del y del v, minus del x del v, del y del u, which is 0 times minus 1, minus times 1 times 1, which is minus 1. So the joint PDF is what? Then the joint PDF. The joint PDF is g of uv, which is mod of j, f of ruv, comma s of uv, and you can put everything. Mod of this will be just 1, and these are independent. So it is f of ruv, and this f of ruv will be equal to nothing but v. Okay, this is our standard notation. This is for ruv. This function is for suv, u minus v, and they are independent, so you can write it as a product, u minus v, and they are both Poisson. So for u and v, so we have Poisson lambda 1 and lambda 2, right? So this will be for x, v for x, that will be for y, for lambda 1, lambda 2. So this will be to the power minus lambda 1 to the power v divided by factorial v times to the power minus lambda 2 to the power u minus v divided by u minus v factorial. So essentially it gives you this e to the power minus lambda 1 plus lambda 2, lambda 1 to the power v and lambda to the power u minus v divided by factorial this v and u minus v factorial. This is how it is defined. Okay. Then you have to find out the marginal one. So now, because we want to find out the PDF of x plus y, okay, which is u here. Question is what is the PDF of x plus y, which is u here. So we found out the joint PDF of uv. You need to find the marginal of u. So now let's say g1 u. Now the PDF of u, the PDF or the marginal PDF of u is this g1 of u. So this you have to take the sum because it is discrete random variable. So 0 to infinity, v you have to vary to the power minus lambda 1 plus lambda 2, lambda 1 to the power v, lambda 2 to the power u minus v divided by factorial v, u minus v factorial. Can anyone tell me what will be this one? Okay, you can take this first of all out, lambda 1 plus lambda 2. This is a series. Sum over v is equal to 0 to infinity, lambda 1 to the power v, lambda to the power u minus v, factorial v and u minus v.
So
Can you
lambda
see
1
any?
v is also
Yeah.
constant.
What? Can you repeat this? I could not hear you.
So lambda 1 to the power v is also constant. Okay, no, v.
Is there? No. Oh, by the way, here we did not mention what is the range of uv. This is sometimes, say u cannot be equal to v, right? So okay, it can be because it is factorial, but we did not say what are the Poisson. What is the Poisson distribution when this lambda 1? What is the range of this? Okay, the parameter here, let's small x parameter, small y. So those are like 0 to infinity, 0, 1 to infinity, and so on. Here we did not say because here v is taking the value x. So and here it is u of x plus y. So we did not say what are these values of u and v. So you have to say this. Can anyone tell me what are the values of u and v? Here. Okay, let me just write it here because we are not going to spend much time on this problem. Okay, so it will be actually, okay, let me write it here. So, I mean, this is a homework. Observe that, because you have to finish this part. Okay, observe that u was this, u is 0, 1, 2 up to infinity. Okay, and v will be 0, 1, 2 up to u. So this will be actually up to u. So, and then you can have this. So this is just a formula, right? E to the power minus, so this is a binomial formula. So this is lambda 1 plus lambda 2 to the power u. Okay, so yeah, okay, there will be factorial u here. Factorial u. So basically what is happening is g1 of u. So this is the PDF of u. E to the power minus lambda 1 plus lambda 2 factorial u, lambda 1 plus lambda 2 to the power u, and use 0, 1, 2 up to infinity and 0 otherwise. So now, can anybody tell me what is this distribution? How does it look like?
Poisson distribution.
Poisson
Yes.
distribution.
So here is the remark. This is a nice thing to observe. That if x is Poisson with some parameter lambda 1, the mean lambda 1, y is Poisson, and they are independent. Okay, and they are independent. They are independent. Then x plus y is Poisson, but what is the variable here? Poisson is just lambda 1 plus lambda 2. So this will help. This kind of results will help you solve some problem probably in the exams. Okay. So you always have to remember this kind of small results. Okay, that can probably be important for solving some problems. Okay, so in general, I mean, there are 2-3 functions which are very fammous. So I'll just, I mean, this is for the sake of solving some problems, okay? So that you don't have to move here and there, also have to solve the entire, you don't have to calculate the entire joint PDF and then what is called the marginal PDF and so on. So I'll just state a theorem for some standard distribution. So wherever you find, for example, in the exam, this kind of function is there, you can directly write the formula, okay? Okay, so let me write it this way. Let xy be random variables. Okay, just a question here. What happens if xy are independent normal random variables? What happens to their addition? Does anybody have a clue? Like here, x and y Poisson, x plus y is also Poisson. The parameter will be nothing but the addition. But now for normal, you have 4 parameters. X is, let's say, mu1 sigma 1, y is mu2 sigma 2. Then x plus y will be what? If it is normal, then what should be its mean and variance? That will be the question. So before that, okay, so just think about it and let me write this this summary of this entire discussion, which can be useful for solving some problems. So let x1 be random variables with joint PDF. So I'm doing a little bit hurry. Joint PDF because I want to finish this today. Then the PDF of x plus y. These are very standard. I mean, in most problems you will see this kind of functions are given. X times y, x plus y, x divided by y. So this addition, product, or multiplication and division are given. So then you can immediately find these results, which you can prove, but I'm not going to prove. As a special case, you can see the proof in the above example, x plus y. So this will be directly, you can write the formula minus to infinity f of u minus v. I think no, this will be v minus u du. This is the formula for x plus y. H of x times y, v, this will be minus infinity to infinity, 1 by mod of u, f of u, v by u times du, and h of x divided by y, this is minus infinity to infinity, mod of u, which you have calculated above, u and uv du. Okay, so these are the formulas. So once you know the f, you can compute what is this. So, and this is valid whether it is independent or not, doesn't matter. If you know the joint PDF, then you have these formulas to compute the PDF for the addition, the multiplication, and the division. Okay, and these are very standard, I would say, standard functions of x and y. Okay, those are useful. Okay, now we'll talk about what is called the bivariate normal distribution. Again, I'm telling you that bivariate Poisson, bivariate Bernoulli, bivariate gamma, bivariate beta, whatever all the distribution you can have, okay, you can study. But we don't have time to do that. It is not also part of the syllabus. So there only the part of the syllabus is bivariate normal. Meaning what? Meaning if you have 2 random variables, x and y, and you have the joint PDF, when do you say they have the normal distribution? It is not that x and y are normal, okay? As a pair, as a joint PDF, when do you call it a normal? Normal distribution. This is the question. Bivariate normal distribution. And this is exactly the generalization of the univariate case, okay? So here is the definition. Definition means I'm just giving you the PDF, okay? A continuous bivariate normal random variable or bivariate random variable So x comma y is said to have normal distribution or bivariate normal distribution. In fact, if you do any course in regression or any high dimensional probability, or let's say multivariate statistics, then it can be defined also for x1, x2 up to n. Here we are talking about a pair, x comma y. But you can have n random variables, and then we can talk about the joint PDF of that n tuple of random variables. When can it be called this normal? Okay, so it's bivariate. So this is the bivariate normal. Okay, if a normal distribution if the joint PDF has 4 parameters. Like standard normal, you had 2 parameters, mu1 and sigma 1. Here we have 4 parameters. The joint PDF is given by f of xy equal to 1 by 2 times pi sigma 1 sigma 2 square root of 1 minus rho square. This rho is playing a role here. Rho is what? The correlation coefficient between x and y. Then e to the power minus half a function of xy. I'll tell you what is the function because this is a long function. So minus into less than x less than y infinity, where qxy is this. It's 1 by 1 minus rho square x minus mu1 by sigma 1 whole square minus 2 rho x minus mu1 by sigma 1 times y minus mu2 by sigma 2 plus y minus mu2 by sigma 2 whole square. It is just like the standard one, but you have 4 parameter one. I mean that single normal random variable, but here you have 4 parameters, and mu1, mu2 here, they could be any real numbers. Sigma 1, sigma 2 are 0 infinity, they are positive, and of course the value of rho is the correlation coefficient, which is minus 1 to 1. But here you can assume this is a parameter. And then we'll say, we'll denote this. So this is the expression, joint PDF for normal, bivariate normal. Okay, so here you see the sigma 1, sigma 2 in this part. Okay, here for the case of single variable, had 2 pi sigma. Okay, 2 pi sigma, and then here a square root of 2 pi sigma. Here e to the power minus half just x square, but here are x minus mu by sigma whole square. But here you have mu1 and mu2 involved, so you have this kind of an expression. As I can see, it is just a generalization. So then we'll denote this. This is the notation. We'll write x comma y followed normal mu1 mu2 sigma 1 sigma 2 and rho. There are actually 5, but you can it will amount to 4. But anyway, so let's say rho is also a parameter here. Is this, and if you want to plot this, so what will happen is, so because here you say x and y, okay, y is also minus infinity. So basically here what is going on, you have this kind of a situation. This is x, this is y, this is 0, but it is extended to minus infinity as well. This is extended to minus infinity as well. Okay, and then there is this z-axis, which is a function of xy. How does it look like depending on mu1 and mu2? Okay. Now you remember, for the case of single variable random normal case, we had some. So these are, let's say this x-axis, this is y-axis. There are some mu, and then it was like a jump here, and then this symmetric along this axis. So, and this spread was sigma. So here instead of mu, it will have some mu and mu2. Let's say here mu1, mu2. Just so they are all okay, whatever, mu1, mu2. And then this will look like a mount, like an umbrella. This is like this. Okay, but it is now spreaded both sides like this. I'm not good at drawing, but anyway. So let us say this is like a mount. So this is like a mount or mountain. MOUNTAI, mountain. This is like a mountain. Okay, and this part, this is centered around. This is the center of the mountain. Center of the mountain is actually mu1 comma mu2. Okay, and sigma square sigma y, sigma square and sigma 2 square. Let's measure the spread along the x-axis and the y-axis. Okay, measure the spread of the mountain, of this mountain along the along the x direction and y direction. Okay, and rho is also a parameter, so rho will determine the shape, whether it is little flat, whether it is little high, and so on. Okay, because I just said it is this one, the center, around it, surrounded by this, there will be a mountain. This is the how much it will vary along this, how much this will vary along this is sigma 1, sigma 2. But I did not say about height of this. Okay, so there will be a shape, like how the mountain is, okay, spreaded. So what is the top and how it is the slope of the mountain alongside this mountain. So this determines the shape and the orientation. Okay, on the xy plane. Okay, so we can just use some standard, I would say, software, or just you can draw it in also in online also. Okay, and can try to see like what kind of distribution and what kind of surface you are getting. Okay. Now the question is, since I know what is the bivariate normal, first question would be what? What is the margin distribution? What is the marginal distribution of x and y? That I did not say. We have to calculate that using this density, using this joint PDF. Okay, but it can be shown. This is also homework. The way we have proved earlier, all the problems we have discussed. So here I'm not going to do that. But if x, the marginal, will actually be normal with the parameters sigma 1 and mu1. So this will be e to the power minus half x minus mu1 by sigma 1 square, and f2, or let's say fy, y is also normal, the parameter mu to sigma 2 to the power minus half x minus mu2 by sigma 2 whole square. Okay. And I can just make a remark here is, if which is obvious from this too, but let me just say, if xy is following normal with mu1, mu2, sigma 1, sigma 2, and rho, then expectation of x is mu1, expectation of y, the marginal ones, 2, variance of x, the marginal one is sigma square, variance of this y, marginal y is sigma 2 square, and the correlation coefficient of xy is equal to rho. And I can also say MGF, because I also have talked about MGF of pair of random variables. So MGF is given by this. MST is e to the power, okay, I think e to the power mu1 s plus mu2 t plus half of sigma square a square plus 2 rho sigma 1 sigma 2 st plus sigma 2 square t square. This is a long expression anyway. So this is the MGF. Okay. Now what the question could be, what is the conditional distribution? What is x given y? Okay. The conditional distribution. So when you study a joint PDF, you have so many things to consider. So conditional distribution. Conditional distribution. So x given y. So what is f of, you can say x given y, or you can here you can write, oh yeah, x given y. This is interesting. This will be 1 by sigma square root of 2 pi 1 minus rho square to the power minus half x minus c by, I'll tell you what is c, sigma 1 minus rho square and then whole square, where c is, can anybody tell me, can anybody remember what is this expression for? Because I talked about this earlier. Does anyone remember what is this kind of an expression? I talked about this in the last class. Okay, this is just a homework to make a connection, whatever I talked about in the last class. So this is x given y. Then you can say f of y given x. Okay, y given x. This is 1 by sigma 2. These are just the formulas. I have to discuss. I mean, I have to write it down because this is a part of the syllabus. That's why I'm writing down. Here, nothing to prove. Why nothing to prove? Because we have discussed all the techniques using which you can prove this. Okay. So we have talked about how to find conditional distribution, how to find the marginal distribution. Using all these formulas, you can just find it out. I mean, there is no big deal about it. So I just have to write this. Okay, and this is very, very important, by the way, for the case of statistics. You'll see a lot of things. Why we are doing it, you'll see why these are all important when you consider statistics. Okay, y minus b, then this is sigma 2 square root of 1 minus rho square, and then whole square of this, where this b will be equal to mu 2 plus rho sigma 2 by sigma 1 x minus mu 1. Okay, so if I just formalize this everything, I can just say, okay, this is just, let's say, remark, set a xy is normal with mu1, mu2, sigma 1, sigma 2, comma rho. Then the expectation of the conditional mean, okay, y given x is mu2. Now, hopefully, you can remember what I'm talking about, this expression. X minus mu1, and expectation of x given y, the conditional mean is mu1 plus rho sigma 1 by sigma 2 y minus mu2, and variance, the conditional variance is y given x is sigma 2 square. This also you can just see the lecture note for the last class. All those expressions we have proved. Y plus 1 minus rho square. So when x, y have bivariate normal distribution, then marginals are also normal. What about the converse? So here, the way we derived it is that we first defined what is the PDF for normal, bivariate normal. This is what we have defined. And why is it called normal? Because it is kind of extension of the single normal random variable. And then we have proved that the marginals are also normal. But suppose the margin, so suppose we have two variables like height and weight, and both are normal. But can I say that the joint will also be normal? That's the question. And it is not the case. Okay, so here again a remark. So that's why I said you before also one day when we were talking about pair of random variables, that if you know the joint from the, remember this for your entire life. If you know the joint, then you can find the marginal. But if you know the marginal, there is no general way to calculate that joint. For some specific cases maybe, but in general there is no formula. There is no way to compute the joint. Okay. Okay. So here, let me just make a remark. Okay, that if xy is bivariate normal, then x and y are normal. In fact, we have seen what will be the mean and the variance. Yeah, here you have seen mu1, mu sigma 1, mu1 sigma square, mu2 sigma 2, sigma 2 square. Okay, we have seen this, but yeah, the converse need to be true. Then x1 normal, but the converse is not true. Converse is not. Okay, I'll give you the homework. Find an example. I mean, find an example means we just take some xy with some parameter mu1, mu2, and sigma 1, sigma 2, and then you try to see that they are joint. I mean, you can have a joint PDF which is not normal, but their condition that their marginal distributions are normal. Can anybody? We have encountered such a situation in this course before. I mean, maybe the last lecture. So can anybody tell me? Can anybody give me an example where you have a pair of random variables whose joint PDF is not normal, but the conditional is normal? Sorry, but the marginal distributions are normal. This is an interesting case. Okay. Okay, so I'll prove one more, not prove, but let me just mention one more result, and from there we can start talking about statistics. Okay, so or maybe we can start statistics. Okay, let us start statistics a little bit today. We have some time left. Okay, now here we'll study statistics, but not in a formal way. Okay, formal way we'll do it next week only. Okay, tomorrow there is no class, by the way. So next week we'll have this formal way of discussing this. But let me start discussing the most famous result in statistics or in probability, which is known as the central limit theorem, or in a broad sense, this is known as law of large numbers. Law of large numbers. Because now we'll be talking about numbers. We have data. Law of large numbers. Okay, let us talk about this. Start from here. Starting from here, we'll go into the statistics part in a more formal way. So let us start with an example. Okay, suppose we are considering a random experiment. Okay, by the way, I mean, since you have holiday tomorrow, I mean, let me give you a problem for food for thought. Okay, I mean, this is just a problem. Okay, because this part we'll be talking about maybe next week or next week itself. I'm just asking you, suppose you take a coin, any coin. Okay, now you want to find out whether the coin is biased or not. Bias means what? I mean, whenever we toss a coin, we always say, okay, probability of success, let's say probability of head equal to something. Head equal to P. And let's say probability of tail is then 1 minus P. But given a coin, you do not know what is this value of P. You don't know. You don't know what is this value of P. So this P is called the bias. If P is exactly half, then you can say that the coin is unbiased. There is no bias involved, okay, in this coin. It's a perfect coin. Now, say, so some people make decision based on this coin toss. The question is this correct way of doing it or not? Will it do justice to your decision or not? Okay, I mean, I should not say justice, because justice is a more bigger term. If you just read the book of Plato, okay, which is written 2005 years ago. Okay, so there is a book called Republic. Okay, you must read this book. Okay, I think this must be available free, or this is not very costly, but maybe 100 or 200 rupees. So there is a book called Republic written by Plato. Okay, 2005 years ago. There you can read his speculations, or his views about justice. Okay? I mean his view in terms of Socrates, who was like, anyway. So the question here is, when you make decision based on a coin toss, so then whether the coin is biased or not, how do you find this bias? What is the value of this P? This is my question. Okay, my question here is, how do you decide? How do you decide the value of P? Value of P. This is my question. So from here we'll start statistics, but not in a formal way, as I'm saying. Okay. Now, so in order to solve this problem, what can you possibly do? Can anybody tell me? In order to solve this problem, find the value of P, what can possibly you do? Anybody want to say something about it? Guys, can you hear me?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Yeah, now tell me, this is like a story. There is no math here involved. Okay, this is like a simple question which anybody can have some views about. Okay, so the question, how do you find the value of P? Hmm? Any idea? I mean, you can say whatever you are thinking. Maybe 1 or 2 minutes you can say. Hmm?
We can carry out many experiments, and from there we can observe that something like.
Okay, so the basic idea here is, this is the idea of statistics. What you say is correct. If it is so, this is about a coin toss experiment, but there may be experiments which you do not know, or you cannot repeat the experiment. That is also possible. Okay, like somebody is having a baby. Okay, whether it will be a girl or whether it will be a boy, you cannot perform the experiment. Okay, many a times. You can't have a guess. Okay, so there we have to deal with the problem separately. Okay, but here, at least in this kind of a situation, you can repeat the experiment. Okay, and then what? Then you can have a data. Okay, so you can repeat the experiment. Okay, this is one way to do it. So you get head, tail, you record all this. Okay, so head can be tail as 1, 0, 1, 1, whatever, 1, 0, 1, 0, 0, 1, whatever you are getting. Okay, you can just record it. So how long will do this experiment? Some number of times you will do this experiment. Let's n number of times. Then what do you do? So this is a general, just common sense. What will you do? Then possibly you will do, okay, how many times out of this n times I got head, how many times I got tail. Okay, that will define my probability of head and probability of tail. That will give a value of P. But this is anyway, this is approximate. That can never be the final answer, because you can increase the value. So suppose you have tossed the coin 100 times, or somebody had tossed the coin 200 times, somebody 1,000 times, okay, and so on. So if you increase the number of increase the repetitions, okay, how many times you repeat, if you increase that number, so maybe you can say that I will get a more precise answer. But still, whatever the number of times you consider, it is finite. can never say that it is the best way to find the answer or it is the final answer. It is always an approximate. Then a theoretical computer scientist will ask this question, okay, or let's say a statistician will ask this question, how much error is involved? So that's a separate issue. Okay, this is what scientists, computer scientists or mathematicians or let's say statisticians will do. Okay, that whatever, let's say 1,000 times, then how much error can be incorporated? Okay, then it can I give you a bound about how much error, okay, is involved in this calculating this probability. You can see, you can do that and think about it. Okay, this is a famous problem. And this we'll be talking about in statistics when we talk about estimation of parameters, because this is a parameter. Okay, now what is happening here is each of these random experiments. So you are performing a random experiment multiple number of times, and each experiment has its own two possibilities, let's say 0 or 1. Okay, but instead of this is a Bernoulli case where you have two possibilities, head and tail. So when you are doing for the first time, you are actually getting a value from that distribution with some probability which you don't know. So now consider this phenomena, consider this example for any kind of an experiment. And if you repeat the process, okay, that can have multiple values as well. Let's say you are rolling a die. Okay, if you are rolling a dice, then what happens? You can have 1, 2, up to 6. Okay, the problem is much more complicated there. Okay, because you have 6. So first time you toss this, so there is a function. So this will appear something like 1, 2, up to 6. But 1 will appear with some probability, let's say P1, 2 will some P2, 3 will some P3, 4 is some P4. You do not know all these values. So something will appear definitely, but you do not know what is the probability. So whenever first time you are doing it, or any time you are doing, let's say the ith time you are performing the experiment, the value of this experiment, like whatever you get, the outcome, okay, this is decided by a distribution. What is the distribution? This P1, P2, value of P1, P2, Pn, okay, what are the parameter is involved, but you do not know the value, those values P1, P2, Pn. Okay, this is a basic aspect of statistics. And suppose you keep on doing, if you have a data, you have drawn the data from somewhere, which is drawn from some distribution which is known, which is not known. Okay, so from tossing the coin to dice and to any experiment, when you are doing for the first time, for the second time, for any time, any nth time, on the ith time, you are getting a value based on a distribution which you don't know, but at least you know the fact. Since you are repeating the experiment under, let's say, identical or let's say under ideal conditions, it is a repetition. And there is again a question. I mean, any scientist will ask this question, and a physicist will ask this question, whether I can perfectly repeat the experiment or not. In a physical situation, in a physical experiment, whether I can perfectly mimic, I can perfectly repeat this experiment or not. This is again a question, but let us not deal with that one. Okay, let us talk about in a broad way, in a classical thing. I mean, for a quantum thing, of course, you cannot do it. But for a classical, let's say I have a very good amount of coin, I mean, good sized coin, or let's say coin is, let's say, at least 20 gram or something like that, so that you can perform the experiment with equivalent. So there is no wind, nothing like that. I mean, everything is very normal. I mean, all are identical conditions. So there are two things. One is, in order to find this value, this probability, okay, first of all, you do not know what distribution it is taking from, it is drawing from. Okay, and if you know that, suppose it is normal, suppose it is binomial, suppose it is Bernoulli, whatever it is, you do not know also the parameters involved. So there are two complexities here. One is you do not know the distribution, and second thing is you do not know the parameters of the distribution as well. Okay. Then the question is, how can I make some conclusion about this data, that this data is drawn from somewhere after a repetitive experiment? Suppose you have a company and you are producing something. Each time you produce that item, okay, it's a random variable. It's coming from the same distribution because everything is identical. But you do not know what is the distribution. You do not know what are the parameters involved. Okay, and you have to make a guess. You have to analyze that data. This is the business of statistics. Okay. So first of all, we'll assume that let x be a random variable. So whatever we are measuring, random variable, yeah, whether it is head or tail or the face of a dice or not, and so on. It's a random variable. Associated with an experiment, or with, suppose x1 is given with the experiment. Okay. And let fx be the PDF, which you don't know, by the way. Okay. PDF. Because since it is random, it must have a PDF. of x. So this is the thing. Mathematically speaking, this is the thing which you are starting with. Here you know only x, but you do not know what fx is. So what you can do is, in order to analyze the data, let us repeat this experiment n times. Okay. Now repeat the experiment because you want to predict what is going to happen. Okay. Next, repeat the experiment. Okay. Let's say n times. So if there is this n times, each time you have the same random variable. First time, third time, second time, third. So each time to perform this, you have the same random variable, but I'm writing it as x1. Second time, same random variable, x2. Third times x3. Fourth times x4. Every time you are, let's say, tossing the point, and so on, you get xn. Okay, and then you get a data. Let's say this is head, this is tail, this is head, this is head, and so on. This is tail, and so on. So you have this data now. So basically, theoretically speaking, you have to perform this experiment for a long time. Okay, but you take a sample, let's say, of finite number of times, let's say some 100 times, 10 times, and so on. Okay. So here, let us first discuss. Let xk denote the random variable associated with the kth repetition. Okay. So then you have this sample. You have this collection of random variable x1, x2, dot 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 xn. Okay. So this is, we will call this as a random sample. Random sample. We'll talk about this in a much more formal way later on. Okay. But since I need to talk about large numbers, so why the large is coming in the picture, n is larger number. That's how this thing is coming into the picture. This is a random sample, x1, x2, xn. Sample of, let's say, size n. Okay. And of course, these are IIDs. Okay. And so xi, I will say, let's say x, I, d. They're all independent and identically distributed, and they have the common PDF fx, where we started with fx. This is the common PDF. So this x1, x2, xn become IID with PDF fx. Now I'll tell you what is called statistics. Statistics in terms of a noun, I can say, or it's called the property. Okay. What is statistics of this data? Okay. Statistics. Now, two things are called statistics. One is called sample mean. What is sample mean? You got these numbers, for example, head, tail. So that's can be, since it's a random variable, you can say this is 1, 0, 1, 1, dot, 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 0. So you always get numbers, right? So sample mean meaning, suppose you get, so x1, you get the value some x1. So x1 is actually x, okay? Suppose it is a die. First time you throw the die, the roll the dice, okay? You get some value. So this value is realized, x1. It could be 1, 2, 3, up to 6, okay? So you get some x1. x2, you get some value, x2, some value. And they are all independent. Yes, you get some value xi. So these are the values you get for x1, x2, xn. You do not know how you are getting the value. What is the distribution that you don't know? And that is, let's say, x. The distribution is fx. Okay, they are all identical, IID. Okay, identical and independent. Then we define sample mean as of these numbers as this. We denote it as x bar, which is 1 by n sum over x1, x2, xn. So I can just write sum over xi, capital xi, I equal to 1 to n. And this is the notation because this is a random variable again, because it's the sum of random variables. It is again, or the combination of random, linear combination of random variables. It is a random variable. But actually, what we are doing is, in order to realize a value, you can say x bar, which is 1 by n, sum over x1 plus x2 plus xn, so x1 plus x2 plus. So once you have performed this experiment, you get this value. But this value can change if you repeat this. Okay, I mean, what I'm trying to tell you is, let's say today you do this experiment, rolling a die, okay, 10 times. You get some value of x1, x2, xn. Okay, tomorrow you do the same thing again. You will get some x1, x2, xn. So this is not a fixed value. This will also change. So that's why this is a random variable. Okay, this is not a fixed number. This is also, x bar is also a random variable. So you can, maybe you can do it for now, right now, this experiment, and then do it again 10 times later on, maybe 1 hour later, and so on. So this is actually a random variable. But once you get those values, x1, small x1, small x2, small xn, then we can have this called the sample mean. Okay, small, so it is 1 by n times x small x1 plus small x2 plus small xn. And now another thing is which we will define is which is called sample variance. Sample variance, which you do not a square. This is again a random variable, but there is a catch. N minus 1, sum over I equal to 1 to n, xi minus x bar whole square. But here you see in the denominator, I mean, this is averaged over n minus 1, not n times like the mean. It is like the tendency towards the center, because x bar is like the mean. Okay, and then x, how much? So xi, so xi minus x bar means it's the distance basically. The square value of this, you can say the square distance. And sum over the distance is divided by n minus 1. Okay, so for example, you can say, suppose you have these numbers 1, 2, dot 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 up to 6. Okay, and x bar somewhere here. You do not know what is it. So x bar is suppose 2.5. It can be 3.5 also. I don't know. It's 2.5. This is suppose x bar. Then the distance from all this, so square distance from all these numbers. Okay, and then take the sum and then divide it by n minus 1, not n. There's a reason to it. We'll talk about this when we'll do it formally. Right now, what we're trying to do is the law of large numbers, meaning when n is large, what is going to happen? What kind of conclusions we can make? That's the question here. So right now, what we're interested here is, what is the distribution of x bar and s square? This is a random variable now. Okay. Okay. By the way, you can have similar value of s square, which is like 1 by n minus 1 for different kinds of realization, 1 to n, xi minus x bar whole square. Okay. We have this realization small square for one kind of experiment. Okay. One day. You can do it next day, next month or so. So this is sample variance. This here it is random variable. Here also it is random variable. So the question is now, what are the distributions of this random variable? X bar, and so sample mean x bar, capital X bar, and sample variance, capital S square. Okay. So right now we'll study about how to find distribution of these two random variables. And maybe we'll start doing it next day because we are running out of time. But yeah, so let us stop here today. If you have any questions, you can ask me.